Nice to see you all. Thank you for joining me. I am an Elixir developer with Interfolio. So Interfolio is a higher ed tech company, and I am on the data services team. So I also am an instructor with LinkedIn Learning, and my Learning Elixir course is coming out around January, just the beginning of the year. It's for beginners, so any beginners you know, send them over in January. And my focus at Interfolio is scholar disambiguation. So today I am going to share with you the challenges of name disambiguation and how I'm meeting those challenges with Elixir. So way back, about 5 days before the World Health Organization declared COVID-19 a pandemic, I gave a talk at the San Francisco CodeBeam conference, and that talk was on unknown unknowns. And I discussed how Austin, I'm local to Austin, by the way, so I talked about how Austin is the home of the very first unknown serial killer. So still don't know who the person was, but talked about this unknown serial killer. But the first time I visited Austin ever was for a much gentler reason. It was for a children's book. So I came to the Ransom Center, which is a library archive associated with the University of Texas. And they have this amazing collection of various things. They have a Gutenberg Bible. They have the world's first photograph. And that's where it is, by the way, if you've ever wondered. It's in Austin, Texas for some reason. But they also have a lot of this guy's photographs. So this is Reverend Charles Ludwig Dodson. And he was a mathematician, studied logic. He wrote about both of those things, but he also wrote about a curious girl named Alice. So you probably know him by his pen name of Lewis Carroll. And he got that pen name by taking his name and loosely translating it into Latin, reversing it, and then kind of loosely translating it back, right? And you would think this is not such a big deal, but Charles rarely admitted that he was the Lewis Carroll. And he went so far as if fan mail arrived to his house addressed to Lewis, he wouldn't accept it because he claimed Lewis didn't live in that house. No one by that name did. So he said it was because he was shy. But the man really liked inventing puzzles. And so I cannot help but wonder if he just liked to puzzle with people as well. And with a pen name like that, it seems like he was trying to irritate someone. But he also left an unsolved riddle behind from Alice's Adventures in Wonderland. And so yes, I'm here to talk to you about the riddle of name disambiguation, but let's start with Charles's riddle first. Why is a raven like a writing desk? So the Mad Hatter asks this of Alice, and Alice says, I don't know, and the Mad Hatter says, me too, I don't know. And so it's never answered in the book, and a couple editions later, Carroll did offer a hint, but he never offered a solution. So in 2014, though, a woman did come up with a solution that I think is the best, and I'll share it with you later, I promise. But for now, let's go back to our riddle, which is the riddle of name disambiguation. So, identifying a real-world person from a name that appears in a publication is a highly desirable feature, but also a very technically challenging problem. So the ambiguity comes from homonymity, which is multiple authors with the same name. So a Vanessa Lee writing in children's literature and a Vanessa Lee writing in biology. You've got synonymity, though. That's where one writer uses their name or writes their name or publishes under different names. So I am Vanessa Lee, but my old boss, Kurt, calls me V. Kaylee, like it's a name. And so you go by different names. And what can help is context, right? And so I have that at work. I know what field they publish in, what journal, maybe they're co-authors, some context that I can work with. But today, we're just going to focus on the problem of synonymity. So we're going to talk about comparing one string to other strings and using Elixir to do it. So that's our riddle. Let's start with an example. So Crossref is the source for publications. You query for a name, you get back a bunch of results. And those results are publications, but those publications have authors. And it's usually a list. Sometimes if you're lucky, it's a list with like, that breaks it down into like first or given name, middle name, surname, but not always. No, sometimes just a string. And sometimes initials. Like it's the last name and then the two initials squished together. Sometimes there's a space. But then you get back these results, and because they use or, not and, between their search terms, then you get back the mess that you get back at the end. And so that is us going down the rabbit hole into name disambiguation, which is really record linkage problem. Record linkage, the process of linking data from one set, an entity, to an entity in other data sets. And you do that with the two-step process of preprocessing, standardizing your data, and data matching. And you can do that data matching either deterministically, lots of rules, or probabilistically, where you get a little fuzzy and you just say, oh, let's throw it all together and see what patterns we find. And that's so intriguing, and it's difficult to pass that, but it can also be trained, right? Like you can learn from it, and so that's going to be the direction we head. So let's take a look at the algorithms. So these are the most common algorithms for string disambiguation, and they kind of break down like this. So you've got the metric, either phonetic, where you break things down into sort of how they sound, or string metrics, which are comparing strings to strings, right? But then you can also break it down further into the sort of unit that they're better at looking at. So are they better at looking at the whole string, the string as a whole, or partial? Do they break it down into tokens or substrings? And all of these, all over the web. But the ones that are best for short strings tend to be the ones that look at the whole string. And the best for sets are the partials, the ones that are better at handling partials. And you would think, okay, names, partials, I've got 3 names, right? And, but sometimes names are short. So actually, we kind of need the best of both. And the app I work on, as I mentioned, is written in Elixir. So I found 2 fuzzy matching libraries out there. And they separately covered most of those algorithms. There was Patrick Detlefson's Fuzzy Compare and John Legler's The Fuzz. But neither library had been updated for a while. So instead of forking them both, I decided to write my own. And so I combined them, added the pre-processing that I wanted, and added one more algorithm that I really wanted to experiment with. It's a phonetic metric called the double metaphone. And writing it in Elixir, because I heard somebody say yesterday, like, why would you rewrite something in Elixir that already exists in another language? Well, I was to learn it, because I wanted to, and it got me familiar with how the algorithm worked. And so double metaphone improves on Metaphone, which was an improvement on SoundX, which was developed in like 1918. It phonetically encodes English words and foreign words that are often heard in English by reducing them to a combination of 12 consonants. And what's neat about double is double. It'll give you 2. It'll give you 2 phonetic representations of a word if it has 2 pronunciations. So now I have everything I want in one library. And I named it Akin, which is derived from kin, which means of similar character, which I thought was funny. But it's also from a book, obviously, my theme. So it was one of my favorite books when I was a kid, the whole series. The negotiations I had with my mom to let me dye my hair red, and she never gave in. And so we don't have time to cover the intricacies of each algorithm together, but I included details in the README if you're interested. It's definitely a work in progress, but this is where it is. If you don't write it down, I'll show it again later. And let's just cover the highlights. So first, the pre-processing. So I called it compose. So compose, it downcases the strings, converts the characters, standardizes and trims the white space, removes punctuation and non-text like emojis, and converts certain accents, and uses a couple of the Erlang Unicode functions. The heart, though, of course, is the comparison. So 2 strings are compared by all of the algorithms, and the metrics for each of those algorithms are returned. And so I get this big long map with results from all of the algorithms. And this one is, yeah, we are in Austin, so we're going to compare weird and the misspelling that I always make. So, which one is wrong? I know. Thank you, Kurt. Thank you. Yes. And you can also get a little fancy with some options. So if you only want to compare using a subset of algorithms, you can list them by name. Or you can use those features we saw in the chart, and you can get just the phonetic ones, or just the ones that are best for partials. And in this case, if you wanted the phonetic ones that are good with whole strings, then you've got the metaphone and the double metaphone. You could also stem the strings, and stemming is where you get down to the root of the word, if anyone studied that in English. And so it's great if you want to compare certain things. So write and writing actually get a perfect score, because at the root, they are the same word. And now we get to our riddle, right? So I actually made a separate function to handle names, two actually. So one returns just the names that match, and the other returns the names that match and their metrics. And that's going to be what we use in our machine learning. So remember, the problem we started with was synonymity, right? So we've got now Alice with her maiden name, Alice P. Little. I've searched for her and received a list of possible authors that match her. You know, and some seem like an obvious match, like that first one, our human eyes go, oh yeah, that's probably the same person. The second one, it gets a little more difficult. But that third, I would say, like, not that person, right? Different last name, different middle name. So let's see, what do the metrics tell us? So in this example, her middle name being spelled out really punishes us with the whole string comparison metrics, right? The bag distance is bad because Pleasance is a lot more letters than P, right? So when we're looking at just the letters, some of those don't score so well. And here we go. Initially, initials were a problem, right? Some of the major publications, like PubMed, is the worst. It's like they go through more trouble to make initials than it would be to just give me the names. But the initial reason for having a separate metric for names compared to strings was because of I needed to give some weight to initials, to when initials match. And one of the nice things that you're going to see here today is that I still haven't gotten there, right? But the machine learning is so, one, it's cool and it's fun, but it also is teaching me sort of where the weaknesses are in the deterministic side of things. So this one, it just makes me hurt to look at these high scores, right? Like my human eyes go, oh, no, no, no. But they're really close, right? They're just 2 letters off. So this is where this is not perfect. So we're going to do the best we can, and we're going to see if machine learning can get us any advantages. And so remember Charles. So he worked in mathematics and specifically in linear and matrix algebra. So yes, he offered us a great gateway into names with that crazy pen name, but he also gives us a nice little segue into machine learning. It's just logical that we do this. So just as a caution, you're about to witness a learning experience. I stumbled, I muddled, but I had a lot of fun doing it. So I used 2 methods. I used numerical Elixir with Axon and Tangram with its Elixir library. So let's just take a quick overview of those. So NX, the multi-dimensional tensors library for Elixir. Axon, powered by NX for neural networks. And in particular, these were the 2 areas that benefited me most, that I focused on in this experience, right? So it was model creation and training. Now, Tangram, which I think was announced really recently, because I heard about it in Reddit, I think the Elixir subreddit. And it just looks so intriguing. And so it's supposed to make it easier for us programmers to do machine learning in that it's going to build the model for us. It's going to take the data, break it into features for me, and train a number of linear and gradient boosted decision tree models and write the best model for me, right? So it also makes predictions with libraries that are already there. So they already have an Elixir library or these other languages. It's written in Rust, it's super fast. And the predictions go over, they're local. So you don't even have to go over the network. This is really fast. But before we can actually dive into the machine learning, I wanted to tell you a little about the data sets that I'm using. So the training and testing data set, much larger, right? So I've got about 9,000 rows. And then I just chose a teeny little prediction set. So what we're basically doing another training though, right? So I'm going to do my training and testing, and then I'm going to test my training and testing, again, with a smaller data set. And the way these break down, so the training data was made with the DBLP data set. So this is like bibliographic information for computer science publications. And it has 4 columns. Same entity, which is Boolean, and it says whether author number 1 is the same entity as author number 2, true or false. Same name, do author 1 and author 2 have the same name? And then we have author 1 and author 2. So here's an example of what that looks like. So the first time, it's not the same entity, not the same name. The next one, same entity, same name. Now that middle one, I extracted that from the data set because that's homonymity. That's not what I'm setting out to solve here. I would need context to solve that problem. So scratch those from the data set. And then the last 2 rows, that's what I'm really after, right? It's the same entity, different names. This is our synonymity. Now, the prediction data set came from an ORCID data set. ORCID is Open Researcher Contributor ID. It's meant to be a unique ID for researchers. Unfortunately, it takes the researcher to actually actively get one and maintain it. And it turns out that's a big ask. So, the data set's great for predicting how well we learn synonymity, though, because they're all matches, right? So it is an author as they appear in publications in these different sources, Medline, ORCID, Authority, and PubMed. And these last 2, those are their name with all 4 name initials or just the first 4 name initial you see on this example. So it's the same author represented several different ways. Examples of synonymity in publishing. So just to make things a little more balanced, I added non-matches. So I made non-matches that matched this format using data that I was using for my testing anyway at work. And then feed all the data sets through the Akin name matching and get a bunch of numbers, this normalized data to give to the machine learning process. So I then have at the very end, that last 1 or 0 represents, is it really a match or not? And that's going to end up being my outcomes column, my target column for machine learning. So let's talk just a little, just as like broad strokes machine learning, right? Training a model means looping over a data set, measuring the loss or how far off the prediction is from the actual truth, adjusting the parameters and looping again. And the epochs represent the number of loops. Loss refers to the method for measuring and handling loss. And learning rate is what increment to use in making changes in response to loss. So I'm going to take about 10 loops through, and I'm using mean squared error. There are so many, and I'm just beginning to learn the differences between them. Started with that one because most people talk about that one, so I can get help on that one easily. And my learning rate, I made it pretty low. That comes from an example that was out there. It's included at the end, so you guys can find the article if you want. This is the repo I used to do these experiments. It is a playground, not a classroom. It is just, it's my mess, and I love my mess. So let's do it. Let's take a look at it. Let's see. All right, so over here, this is the Axon library. So this is using Axon. It's a little module for Axon that is going to train my model. So let's watch it. So it's going to go through these epochs, and each epoch is going to go through that data set, and it's going to tell you its loss, right? And I'm not doing a ton of epochs, so we're not going to see, when you do run like a ton of epochs, it's really nice because you can see that loss like go down consistently and beautifully. Like it's really nice to watch it learn. But with 10, it's a little hard, it's a little sporadic in the beginning. But we are going down though. That's nice. Sometimes they'll pop back up. But we're on epoch 7. Maybe not everyone likes to watch this as much as I do. And I did use color coding in the results, so we should be able to see the ones that make me happy are green. And those are that the actual and the predictor match, like this predicted probability, looks pretty impressive. And, oh, there we had one. That one was an actual yes, but I'm not happy with that probability, right? Seems a little low. But honestly, so what can I do with all of this? I mean, I could turn this into graphs. I can make this better. I can keep learning. I can keep training. I can get better data. But this is pretty good, right? So now let's take a look at Tangram. So I've got my server running. And this is where I'm going to train. So that I'm going to train a model based on the same data set. And my target is that 1 or 0, right? So, okay, I'm just spoiled by the graphics on this one, y'all. So they're just giving me such nice feedback. And the little train, that's not lost on me. That's cute. And this is just going through, computing the different features from the data set on its own, going through and using several different models, landing on the best one, and then it's done. And so it tells me where it's put the file that we can use. And to use it, to use the model, so I have this like backup one in case this doesn't work, but let's create a new one just to use the one we just created. So we'll call this one Alice. Okay, so we'll upload a model. It's spinning. Let's go over here and start doing some predictions. So this is the command for writing the prediction. And it's going to give me some nice little outputs too. So it's going to compare these names and give me probabilities. And it was a smaller data set, it's only like 100. So that went pretty quickly. And it tells me whether it thinks it was a match and how confident it is. And this one, it's not uploading. Well, let's not let it get in our way. Let's see. Oh, it'll be unfortunate if you can't see it. Let me see if I go to my backup, because the fun is the tools that Tangram gives me. Let's go over here, and I'll show you my backup. Okay. So this is the same model I just ran before starting the talk. And do not be fooled by how wonderful this looks, right? Like, it's 100% accurate. It's so great. It's so good. But I learned why you don't trust that. And then, oh, sure, it looks great. And this is kind of neat to see how that loss falls. And this is so much fun, right? I can see which of my features were the most influential, right? I am surprised that bag distance ended up being so influential. And pay no mind to how low on that scale my algorithm is. It's just not very influential, but what are you going to do? And so then you can see exactly what that feature importance value is. And we can play around with different aspects of the features, looking at what hyperparameters were used. I can look at the statistics up close to see how many unique values, the mean. And these are nice too. Now here's where you get into, this confusion matrix. So this isn't so bad. Only one false positive, which I think recall is called recall, but that confuses me because it doesn't make sense now with the recall. That's not what that word means. But it's not bad. It looks impressive. And this is the fun part too. They give you this playground where you can do exactly what I said. We can change. Like if we wanted to, we can go like, let's go give these some like really low numbers. Like if we go, who else has a high one? Yeah, let's knock this guy down to like 2. And anybody else? Yeah, you'll go down. Let's put you at 3. And then let's give my Metaphone a really high score. Let's do like 9. And let's run a prediction. And I still can't fool the algorithm. No, I'm sorry. It's not great. And so one of the other things that's really nice is that when you do load in some predictions, you can drill down. You see your output, But then you can also drill down and see what the actual values were. You start to identify problems. It'll give you its probability. It thinks it's a match, but it's not very confident that that one's a match. And so, oh yeah, I can see why, right? That's a tough one, but it did make the right call. And I can also then upload the truth. So I can then tell Tangram what those predictions should actually be. So in production, if I knew what I should expect at some point, then I can have a true value count and see that my production accuracy, although less than my training accuracy, still pretty respectful. But truth be told, when I run it through like a really small data set, it's really bad. So it really depends on what you've got. There's sort of safety in numbers, I think. You can look better. So what I have learned is, I don't know if you noticed, I scrolled by it pretty quickly. But back here in the training data, where was it? Overview. My initials had no weight. And so it's a Boolean that says, do the initials match, do they not? Not good here, not being used. And a lot of the times that it fails, it has to do with that. Like it's not picking up on initials that are the same or initials that are different. And so that's what I'm going to be working on next. I need to see if I can improve. Obviously, a Boolean isn't getting me there. So only 26 letters in the alphabet, right? Like I just send the initials and see what happens and see if it notices anything there. So that's what I'm going to play with next. So let's see. I have no idea where my presentation went. I have lost it. There we go. Yay, okay. All right, so I gave you some of those. So what else is next is that I've got a common misspellings data set that I want to run through it. I just didn't have time before the conference. And because I'm a glutton for punishment, there's another algorithm I want to write. And this one is the Levenstein Distance. It's like Levenstein, but it actually transposes the characters, so you can catch some common misspellings. And if you notice that misspellings come up a lot, it's because a lot of authors enter their own names into our system. Yeah. So I did not forget that I promised you an answer to the riddle. Why is a raven like a writing desk? But I wondered if anyone had an answer. Yes.
Oh, wrote on both.
That was my answer. Yes. Hers is better, but I thought that too. And those just Jabberwocky and the Raven happened to be the poems I memorized as a kid, so I could recite them if you wanted me to. So this was Mary Hammond's answer in 2014. I think it's pretty stellar. So we get the last laugh on Charles. But thank you for coming to my talk. I've really enjoyed having you here.